Yes, good morning, everyone. Yes, we'll continue with the last topic in the communication interface, that is general packet radio service. See, just to give some brief information about this GPRS, it's a very old technology which was there during the 2G technology, which was used in 2G. For what purpose they used is it is for uh, audio and video data communication. Totally, it is for transferring the data over the our mobile communication network. They used to use this GPRS. How they used to send? They used to send using the packet structure. If you see the transfer rate, or if you have used the 2G mobiles, then you would have seen the download speed of maximum in the range of kbps itself. A very slow network. The maximum transfer rate you can get is 171.2 kilobits per second. See, very very less. Uh, the what the maximum the transfer rate. That is why this GPRS, as slowly they have removed from the 3G. Now 3G network, the third generation, it is going to be removed, and also uh, third generation will also be removed. Along with that, the GPRS technology will also be removed. How they used to do in the GPRS communication is they used to use the radio waves. 100% they have moved from infrared to radio waves. They have not used any other type of waves. Okay. In the radio waves itself, what they have done is they have divided into channels. In those channels, they used to send the data. There will be a separate radio channel for a separate cell phone user. In that channel itself, they used to send, and that each time channel it will be given some time slot. In that time slot itself, the user is going to send. Okay, that radio channel it was divided into number of slots, and for each slot, for each channel, there was a separate time slot. Example, some 10 or 20 millisecond. In that 20 millisecond, as a my Nandish, my mobile data will be sent. In another time slot, another user. In that way, the channel was divided. Radio waves channel was divided. In that time also, the internet protocol was there. That's the GPRS was to support this internet protocol, X.25 protocols or point-to-point protocol for communication. If we say internet protocol means there was a concept of IP address. There was the concept of IP address was there in the GPRS also, because there is a packet. Packet structure means there will be a IP address. Okay. Uh, that now the GPRS is very old technology. Over the time, it has been evolved with so many techniques called edge. After that, high speed downlink packet access. Now, whatever the 4G technique, what you see, long term evolution, LTE, these are the which provides a very high bandwidth for communication. These are all it provides the high bandwidth for communication. You can see, observe the download speeds in terms of megabits per second. See, in 2G it was zero point 0.1 megabits per second. It is bytes per second. But see, in 4G it is almost 1 GB or 929 megabytes per second. Now we are going to get a huge amount in 5G. See, whatever the numbers you see here, that it is totally different in India compared to the other countries. The 4G speed in India is different. The same 4G speed in other countries it is different. For that, so many other reasons are there that we are not ready to discuss. But 5G it is going to bring some more fast speed in the data access. That is for sure. Okay. The next part, the next part we are going to discuss after the communication interface is this embedded firmware. What is this embedded firmware? Means Till now, we have discussed some of the buses, some of the hardware component. Now we should see some of the software part also, right? Some instructions, some control algorithms, which controls the hardware inside that. Okay, that program we are seeing. This embedded firmware is nothing but, you can call it as a control algorithm, you can call it as instructions or anything that will be there inside the embedded system, that will be there inside the memory of an embedded system, that we call it as an embedded firmware. Is it clear? What is this embedded firmware? Embedded firmware is nothing but, it is a program instructions, or indirectly you can call it as control algorithms. Where exactly that will be? It will be inside the program memory, in the memory of an embedded system. That is going to control the all the hardwares. Okay. Without this embedded firmware, you cannot find the existence of an embedded system. It is must and should. With only the hardware, can you do anything? No. Okay. In order to develop those programs, control algorithms, which are the languages are there? There are so many languages are there. In that, the most famous is embedded C or C++. All those things where we can type, those we can type, edit, simulate, run, debug, everything in the Keel software. That is one of the integrated development environment. For any softwares, we don't simply call it as an editor, we call it as an integrated development environment. When we call that is, it should contain, editor should be there, compiler should be there, linker should be there, debugger, simulator, testing unit should be there. Everything, if it is there, totally that software is called as integrated development environment. See, Eclipse, which is used to develop the Java programs, then that is called as integrated development environment. Okay, this Keel software, which is called as an IDE, that will help for writing the microcontroller functions. Whether you should write only this high level language embedded C, no, even you can write the assembly language program also to perform the some function. C program ಬರಿಬೇಕು ಅಂತಿಲ್ಲ, you can write the assembly language program also. Okay, what is an advantage with high level, or what is an advantage with assembly language? See, directly what the machine can understand, it can understand only machine codes. For that reason, you require compilers. There will be a compiler which converts high level language to machine code. Okay, that machine code we are going to call it as an hexa file creation. Then that hexa file, hexa file creation, if you compare with the different programmings, the different compilers will generates different hexa file. Finally, the task will be same, but if you check the compilers for in different architecture, they create a different hexa file. Means we are talking about binary code, machine readable binary code, that we call it as an hexa file. Okay, there are so many tools are there that are available, uh, where which you can convert your assembly language code to the machine language code. Okay. Finally, the program what you write there, that will be compiled by the compiler. Then the machine readable code only, that hexa file, that only it is required for the hardware. That if you dump, it is enough. If you directly dump the hexa file to the hardware, that machine code, that is enough to run. This you are going to come across in the lab, how to give the hexa file in the Keel software to any hardware. That you will come across in the microcontroller lab, LPC 2148 microcontroller. In that, how to give the hexa file, binary file, and how exactly your microcontroller peripherals will run. That you are going to see it in the lab, or how the hexa file will be there. All that structures you can see it in the lab itself. Well, finally, what is an advantage with the high level language? It is easy for any developer to start with C, C++ compared to the assembly language. In order to debug also, it is easy for portable. It is not developer dependent. See, if I say one word called the program written in the high level language, it is not developer dependent. Why? The meaning is, if I ask you to check the condition whether A is greater than B and A is greater than C and print the message, you will use some two if condition and one else. Okay. If I ask any other person, he'll write the same thing. But if I ask to write it in the assembly language instruction, a single instruction can be written with two or more instructions. It is based on the instructions he selects. That is why we say high level languages is not developer dependent, but assembly language it is low level, it is developer dependent. He can take single instruction, he can complete. Like example, MLA, multiplication and accumulate, or else you can use multiply and then addition he is going to do. Okay, that is why which one is better, that the programmer has to choose. Finally, these high level languages, uh, for overall system development and also for debugging, it is very easy compared to the assembly languages program. And also to learn the assembly language programs, it is very difficult also. That you have come across. If you have learned C, and now if you have seen the instructions of a ARM microcontroller, you should differentiate which is easy and which is difficult. Okay, by now you should know which is easy and which is difficult. Okay, how if there are some programs, okay, inside the uh, as I said, inside the microcontroller memory we put these control algorithms. Whenever we put these control algorithms inside uh, the the firmware, sorry, whenever we put this control algorithm inside the program memory of the microcontroller, repeatedly the same program it is going to work from step 1 to step 10. After that, once again go to step 1, execute. If it is a single program, continuously the same program it is going to repeat. If you see the program of a stepper motor, that stepper motor same program will be run multiple times. That is why you see the motor continuously it is going to run. Okay, in that way the control this control program, the first type of control program development, it is like a infinite while loop that you can directly relate with the C program. It is infinite while loop, means it will start executing from top to bottom. Once again go back to the first line, start executing. Okay, in that way you have this control algorithm program that you have to develop, or else you are going to divide the task into separate functions, and now the scheduler will start executing those tasks one after the other. If you complete all the tasks, once again come back to the first function, first task. Task 2 execute, task 3 execute, task 4 execute, come back once again to task 1, task 2. In that way it is going to execute. In that way also you have to develop the control algorithm. In two ways there can be embedded firmware development. Okay, now we are going to discuss about the other components other than the communication buses, the software, or the hardware, the whatever the devices, optocoupler, so many devices we have discussed, right? Other extra peripherals that will be there on the microcontroller, it can be internal or it can be external to the microcontroller. See, some of them are watchdog timers, reset IC, brownout protection IC, or the oscillator. These are the some of the other system components which are there on the embedded system. Which are there on the embedded system. Okay, one by one we'll see. What is this reset circuit? The first one is reset circuit, then real-time clock, then watchdog, and oscillator we'll discuss now. What is this reset circuit is, see this reset circuit, what it can generate is, it can generate a reset signal. What it indicates? It is going to indicate so many information. Whenever the power is applied to any electronic device, some electric signals is going to be sent. What that indicates to the processor, if it is sent to the processor, what this indicate to the processor is, if the device, if it is not working at, if the particular device, if it is not working at an certain voltage level, then it indicates no need to continue with the work. It should not do the work. If any device gets the a signal, reset signal, it indicates that there is some problem. Whatever it is required, the desired voltage level is required, that is not there. See, this is must and should on the microcontrollers because there is a scarcity of power problem. Because since it is a portable devices, there will not be a continuous power supply. All these are battery operated. Okay, that is why if there is no uh, exact desired voltage level for a device, then this reset circuit will generate the uh, resetting signals. Based on that, the actions will be taken by the processor. This reset signal can be active high or active low. Means whenever there is a high signal, it indicates there is a problem. Or whenever there is a active low signal, that indicates it's a reset signal. Okay. See, if this type of devices, if it is, it can be there internally inside the processor, or you can get it externally also. Some processor, it will have a built-in reset circuitry. And if you don't have, then you have to bring external reset circuitry. What it contains inside that IC is example in the form of IC you are going to get MAX810. MAX810, that is a IC which generates the reset signals. Internally, what it contains? It contains simple a capacitor and the resistor. See here, the capacitor and the resistor. If the reset circuit, if you want active high signal, the circuit will be like this. See, one diode parallel with the resistor and one capacitor. And here, see the capacitor. If you want the active low signal, if you don't have a desired voltage, in that way, it can generate an active low signal. This will generate the active high signal. Based on this active high signals, the device will take necessary actions after that. It is just an indicator. Reset circuit, it is just an indicator. Internal components of the circuit, it contains only a capacitor, diode, and a resistor. A capacitor and a resistors are enough to design any reset circuit. Most of the processor will come with the inbuilt reset circuit. If you don't have, as I said, there is an IC is there, MX810 IC, that is a standard reset IC that may be connected on the that may be interfaced with the processor. Interface is nothing but it may be connected with the processor. Okay. Hmm. The next thing, one more circuit, blown out protection circuit. This circuit, it will help it may be inside the processor or maybe outside. Okay, that you should remember. It should not be always the outside the microcontroller. It can be inside also. Okay, what is the job of this? See, whenever there is an execution of the program, if there is no problem of a supply voltage, it is going to execute properly. If the desired voltage level is not the specified voltage, there is a chances of executing wrong program, or it may end up with unexpected behavior. Okay, if it requires some plus 12 volts, okay, for the normal execution of the processor, if it requires the desired voltage level as some plus 12 volts, if it is not there, since it is battery operated, there is a problem of battery. Okay, battery voltage is very low. In that case, there is a chances of unexpected behavior. Okay, in order to control this, the processor behavior, it is not predictable. Okay, when it is below the voltage level, that is why we require some circuit which regulates this. Even you can use the reset circuit for this also. If you don't have a proper voltage level, even that will leads to the data corruption also. Okay, that is why this brownout protection circuit, it will holds the processor. It can be the processor or so many controllers are there, right? Memory controller, this interrupt controller, all those devices. It can be any other components. It will hold them in the reset state, means it cannot do anything. The processor, it cannot do anything. It holds. The reset state informs. It stops now. The brown state stops the processor until it below the voltage is below the threshold. It stops. When it crosses the threshold voltage, then the processor can continue its execution. Okay. Therefore, what the brownout protection circuit will do is it continuously monitor the supply voltages. If it is internally, it is an internal component. If it doesn't have built-in, then you should go for IC, the special ICs which control the processor. ಪ್ರೊಸೆಸರ್ ಒಳಗೆ ಇನ್ಬಿಲ್ಟ್ ಬಂದಿದ್ರೆ ಪ್ರಾಬ್ಲಮ್ ಇಲ್ಲ. ಇಲ್ಲ ಅಂದ್ರೆ ಈ ಬ್ರೌನ್ ಔಟ್ ಪ್ರೊಟೆಕ್ಷನ್ ಐಸಿ ಮಾರ್ಕೆಟ್ ಅಲ್ಲಿ ಅವೈಲೇಬಲ್ ಇರುತ್ತಲ್ಲ, ಅದನ್ನ ಆ PCB ಮೇಲೆ ಕನೆಕ್ಟ್ ಮಾಡಬೇಕು. ಪ್ರಿಂಟೆಡ್ ಸರ್ಕ್ಯೂಟ್ ಬೋರ್ಡ್ ಯು ಹ್ಯಾವ್ ಟು ಕನೆಕ್ಟ್. ಓಕೆ, ಒನ್ ಮೋರ್ ಕಾಂಪೊನೆಂಟ್, oscillator unit. You have seen yellow pins on the motherboard, sorry, trainer kit in the ADE lab, which generates clock signals. In the same way here, in order to generate the clock signals, clocks for the processor, clock input for the processor, who is going to generate? This oscillator unit inside the embedded system will generate this clock. See, without the clock, your processor will not execute. It is like a timer. For us, it is an heartbeat, right? Which produces heartbeat. Then only you can work, you can survive. In the same way, without the clock input, your processor will not execute the instructions. Okay, this is what this clock. It is a small amount of time. It's a very small amount of time. As our resource person Arish Makali was saying, if it is a 3 gigahertz, then you can take that one third of the nanosecond. Sorry, one third of the second. No. It's one third of the nanosecond. Okay. It is very small time. In that small time, the processor will start executing each instructions. Okay. This oscillator circuit, it is going to generate the clock input. What is there inside that clock input? There is some hardware. Always the processor will contains this built-in oscillator circuits are there. Which is the part inside that hardware? Which is that hardware part which generates the clock signals are this ceramic resonator or quartz crystal. Okay, they are the components which generates the clock signal. The ceramic resonator or the quartz crystal, any one, they are not both, in any one, both will generate the clock signals. Physically, the components, what is there inside the quartz crystals or ceramic resonators are different. Finally, the operation is the same. Okay, what is this oscillators? It generates the clock signals. If these devices, if are not there inside the microcontrollers, what is the next thing? It should be interfaced with the processor. How? In the form of a chips that you have to connect it on the board. The next question is, if we get access for the clock, now whenever as I already said, it is in the form of chips. Can we directly bring high frequency clock and connect it to the processor, and which will increase the speed of the clock, our processor? If you think in that way, it is not at all possible. ಕ್ಲಾಕ್ ಸ್ಪೀಡ್ ಅನ್ನು ಸುಮ್ಮನೆ ಜಾಸ್ತಿ ಮಾಡಿ, ಇಲ್ಲ ಜಾಸ್ತಿ ಸ್ಪೀಡ್ ಇರೋಂತ ಕ್ಲಾಕ್ ಅನ್ನು ತಗೊಂಬಂದು ಪ್ರೊಸೆಸರ್ ಜೊತೆ ಇಟ್ಟಿದ ತಕ್ಷಣ ಇನ್ಸ್ಟ್ರಕ್ಷನ್ ಎಕ್ಸಿಕ್ಯೂಷನ್ ಫಾಸ್ಟರ್ ಆಗಲ್ಲ. ಓಕೆ, the speed of the operation of the processor, that is dependent on the clock frequency. Okay, both are dependent. If I say, even if I say some topics in 1x or 2x speed, okay, or not all the students can understand, some of you can understand. If I increase the 2x speed, okay, everyone cannot catch it, all the words. That is why there should be a synchronization. That is why the speed of the operation of the processor, that is always be dependent on the clock frequency. If you just simply increase the clock frequency, that will not increase the speed of the execution. Okay. And also see the total system power consumption, it is always directly proportional to the clock frequency. If you increase the clock frequency, if it is faster, clock frequency is more, means power consumption is also more. See, one more dependency. If the accuracy of the clock signal is good, then the accuracy of the program execution is also good. The components, the accuracy of the crystal oscillators or ceramic resonators, that will say in terms of parts per million. See, that is what it is, completely internally to the oscillator. Finally, from outside, it will generate some clock signals. That's all. This is what the diagram of the quartz. See the crystal resonator. See this one. It can be. This is internally to the microcontroller. Inside the microprocessor, outside also you can connect. See, it sends clock input. This is a clock input, means clock signals are sent. Inside the microcontroller, it is there, oscillator unit. With the microprocessor, we have connected the oscillator unit. You have one more real-time clock. This we have seen. Whatever the time I am seeing here, 10:30 now. At 10:30, it is because of this real-time clock itself. See, this real-time clock, it will keep tracking the time. See, it holds the information like current time in hours, minutes, and seconds in 12 hours or 24 hours format. Okay. And this clock, even if I shut down my system, that clock it is going to run. How? It is a battery operated. There is a CMOS battery will be there. That CMOS battery that will help you to run the clock. Okay. And this real-time clock, it's a circuit. Okay. That is readily available in the form of ICs now. Who is the vendor? It can be Maximum Dallas or ST Microelectronics. These devices, these RTC chips, even you can interface that with the processor or the controller of the embedded system. This same real-time clock you can interface, you can connect to the embedded system. ಈಗೇನ್ ನಮ್ಮ ಲ್ಯಾಪ್ಟಾಪ್ಸ್ ಅಲ್ಲಿ ಇರುತ್ತೆ ಅದನ್ನೇ ನೀವು ಎಂಬೆಡೆಡ್ ಸಿಸ್ಟಮ್ಸ್ ಅಲ್ಲೂ ಕನೆಕ್ಟ್ ಮಾಡಬಹುದು. Okay, even you can connect that in the embedded system. Whether it is required, yes, it is required. These RTCs, they are required. Why this timing concept is required? Without the time, whether your operating system will not work? No. For synchronization of the operations of the operating system, the timing is necessary. Okay, if any problem is there, if any problem is with the timer, then this circuit, if it doesn't have a proper timings, means time is not set, then even you can interrupt this circuit, the real-time clock circuit, it is going to interrupt the OS kernel. It informs, it requests the processor to reset. then what the OS, the operating kernel will do, it will see the number. It will see the number for which it is generated. There will be a unique number for the real-time clock also. Okay, with that number, it is going to perform the next action. What action? It is going to update the system date and time or any other software timers. Whenever there is a real-time this RTC timer interrupt occurs. With the interrupts, even you can reset the, or you can update the system date and time, or you can manage the software timers with the which interrupt, with the RTC interrupt. There will be a RTC interrupt line also, through which you can send this interrupt to the processor or to the any other controller. Totally for what purpose we use this real-time clock? See, if you want some time information, it is required. For synchronization of the operations of OS kernel, it is required. If this real-time clock is not been set, what is the next thing? We use interrupts to update our system date and clock. Whether there is a separate interrupt line is there to communicate? Yes, it is there. Yes, this is all about this real-time clock. In the same way, there is a one more timer called Watchdog Timer. There will not be any dog here. It's a timer, means it is like a counter. It is simply watches. It's an hardware part. It simply watches the execution, some instruction execution. See, without the time concept, an instruction cannot execute. For each different processes, for each a specific time will be given. 100 instructions in 5 seconds, or 5 instructions in 5 seconds. Okay, in order to implement that watchdog timer, what it contains the counter value. There are two types of timers, watchdog timers. One can be the increment up counting watchdog, and the another one is down counting watchdog. There will be a counter variable. That counter variable, if initially it will be initialized in the reset, in the first state, reset state, it will be initialized to 0 in case of up counting watchdog. Then the counter starts incrementing. Then once it reaches the maximum value, some 5 seconds, yes, it informs the processor this time is been reached. Then it shifts to the other process, because the processor cannot execute only the instruction of one software, one application. It has to execute the instructions of other application also. Some specific time will be given for each application. That time will be indicated by this with watchdog timer. In case of down counter, it will be set to the maximum 5 value, starts decrementing. 5 seconds, the maximum value will be set. After that, 5 instruction. In order to execute 5 instruction, assume that 5 seconds are required. 5, 4, 3, 2, 1, 0. The watchdog timer will indicate processor. Okay, the time which is given for this process, it is enough now. Next you can move on to the next other process. It just indicates the time is over now. In order to store that, the timer counter variable, there will be a register. Watchdog timer register will be there. That we are going to reset to the 0, or we are going to reset to the maximum value. Finally, it will help you for execution of the instructions. Some maximum value it will be reset, or some minimum value it will be reset. If it is inbuilt, if you have a watchdog timer inside the processor, no problem. Or else you have to use the external. What is the IC number? ICDS1232. That is a hardware watchdog timer IC which is available in the market. That you have to connect. Once the time is over, what it happens, the interrupt will be raised, that will be informed to the processor. See here, the watchdog timer, that will inform to the microprocessor. You have to this the time which is there, it is over now. So you can take the next actions. There is a register inside that. This is what this register which have a counter variable. Okay. The last topic in this is PCB and passive components. What is this PCB? Printed circuit board. See, this printed circuit board, it is a place where all the components are placed. It's a board. It's a backbone of the embedded system. Okay. How to prepare this PCB? First, we are going to do all the work on this sheet of paper where we are going to place the microprocessor, where we are going to place the peripherals, and then how the buses are connected. Everything, the sketch will be drawn on the sheet of paper. In a single sheet, that sketch will be done, and then it will be manufactured. That PCB will be fabricated. That schematic design will be done first, and then it will be fabricated. Okay, all the components, it will be, the PCB will holds all the necessary components of an embedded system. Inside that itself, we are going to place our embedded firmware. Whether it is only the microprocessor, the peripherals will be there on the PCB. With that, there will be resistors, capacitor, diodes, everything will be there. Okay. Without that, you cannot say that a proper one, it will not properly work. If you want the proper functioning of an embedded system, you require all those things: resistor, capacitor, diodes, microprocessor, the memory, the other peripherals, the reset circuit, everything. Okay. The power supply, voltage slots, everything is required. In order to place that, your PCB is required. On that itself, everything will be mounted. Okay. With this much of information, I'm going to complete this module 3, and from the next class, we will start module 4. Okay. Thank you.